All right. This is sort of like our official last lesson of Calc AB. Congratulations. You've made it. Uh, and this is really just kind of an application of ideas that we already have been using, but kind of a little more complicated, applied to sort of larger problems. So this is usually you're going to get something like this on free response. Anyways, just a sort of I guess, a silly anecdote. Spring cleaning, my wife has, got rid of some of my clothes, but then I bought a new shirt. So today, my closet, this is kind of like the fundamental theorem of life, right? Today, my closet is different than yesterday. Today, it is what it was, minus the clothes that I gave away, plus the new ones that I bought. Fundamental theorem of calculus of the closet, FTC, right? Anyways, the big idea here is that we're using fundamental theorem of calculus, that idea that, the amount now is the amount before plus all the changes, which is the integral of the derivative. But now we're going to have incoming changes and outgoing changes. So there's going to be two different rates involved, two different derivatives. And we're usually going to be applying these to kind of like more real world scenarios. So here's just another simple example, and we'll kind of build off this. And then on the back, we're going to do a free response question. And you can kind of see some of the typical questions that often come up with rate modeling. So this is called rate modeling. So let's say that you live on a property where you have a water well. Some of you guys might be able to relate to this. I don't specifically relate to this personally, but I understand the idea. So you often have a tank to hold the water, and you got to pump water out of the well into your tank. And, maybe there's some trigger that'll stop it once the tank's full. So you got water coming into the tank, but you also are going to be using water, throughout the day for different purposes. And so water is going to be leaving the tank. So the amount of water in the tank is going to be dependent on both what's coming in and what's going out. So the current amount at some later time too is going to depend on the amount that we had earlier. So there's some known amount at some point, that's like an initial condition, plus the integral of the derivative of what's entering. So I'll often use maybe a capital E for entering, but we want to accumulate all the water that entered from time 1 to time 2. So if you integrate a derivative, it gives you a total change in the amount of the thing it was measuring that was changing. But then we also have to subtract the leaving rate. Leaving rate will often not have a negative associated with it, so you're going to have to put the negative there. So we want to integrate the leaving rate to figure out how much water was lost. Now, just from a unit analysis perspective, this should make sense. If we're talking about water, gallons, so we had gallons initially. The entering rate is going to be gallons per hour, right? Gallons per hour. dt matters. dt is change in time, which is hours, and that kind of shows you we should get gallons from that. And this is gallons per hour also, but then dt is hours, and so we should get gallons from that. So all these kind of make sense from sort of a unit analysis approach. Now, let's go ahead and take this example, and we'll go ahead and give it some more actual numbers and kind of investigate what's going on and what kind of questions we might ask, what kind of questions we might try to answer. So let's say that the entering rate is just constant, 100 gallons per hour, which might be kind of realistic, that a pump probably pumps the same amount of water all the time. I did talk about that. It might shut off when the tank is full, but we'll just ignore that idea. The leaving rate, we'll say, is not constant, but we're going to make a really simple function, just a linear function, 10t. T is time. The initial amount at time 0 is 5,000 gallons. So we got to know some initial amount. Now, let's just graph these two rates together and see what it looks like. So the 100 gallons per hour, that's just a horizontal line. So that's a graph of the derivative. So we're graphing derivatives right now. The other one is 10t, which has a y-intercept of 0, slope of 10. I'm just drawing this kind of roughly. This is the leaving rate. This is 10t gallons per hour. And yeah, so I mean, we can't graph the 5,000 on here. That's the amount of water, whereas these are derivatives, so it wouldn't make sense. So we're graphing derivatives per time. Now, often on these problems, they're going to give you some kind of constraint, like over the course of a day, or from 9 p.m. to 12 p.m. or whatever. So on ours, we'll just assume 24 hours, so just over the course of a day. So those are going to be something that we're going to use later. Those are going to be endpoints. Probably going to have to do extreme value theorem. Is pretty common on these rate model problems. Now, just going over here, could we figure out how much is in the tank after 4 hours? Now, I'm making this multiple choice, but let's think about maybe you try and use the graph. So let's see. Let's try and find this intersection right here, because I feel like that seems to be sort of an important change. You might consider right here that there is more water coming in. So if we integrate the rate, which we showed up here, the derivative, that integral gives you the amount of change in the water. So the area under this curve represents all the water that came in, and the area under this curve represents all the water that left. The difference is going to be the difference in the total amount of water in the tank. So there's more water coming in than leaving. So the level of water in the tank is going up and up and up and up. But then after this, the level of water is going to be going down because more water is leaving. The area under this line is more than the area under the entering line. So the water level is going to go down. So this is kind of an important place where the water is going up and now it's going down. So that's probably going to be somewhere near where maybe where we have the most amount of water in the tank, which might be a good absolute maximum question. But where do these intersect each other? So 10t equals 100. You guys should be getting good at finding intersections of curves again. We've been doing them a lot with the area and volume problems. So that's going to be at time 10. And if you plug 10 in, you get 100 into either one of those. So we're specifically interested in 4 hours. So that's going to be somewhere like around here. And so what we could do, so what are these coordinates of these points? This is 0. This is 40. This is 100. Those values might help us find some things. And so I was already talking about how the area under these curves actually represents how much water is coming in, how much water is coming out. So the area of what came in from 0 to 4 hours, well, that area is 4 times 100. And so that's 400. 400 gallons entered the tank from time 0 to time 4. How many gallons left the tank? Well, that'd be the area of that triangle right there. So that's going to be 1/2. Base is 4. Height is 40. So those coordinates are coming in handy. And that's going to be 80 gallons left the tank, right? But we also need to consider how much was in the tank to start with. So there was 5,000 gallons at time equals 0. So we have 5,000 gallons. We're going to add 400 gallons, but then we've got to subtract 80 gallons. So that's going to be 5,320 gallons total. Okay? So that would be our answer. So that's kind of giving you a preview of like, things that we could do with this rate model. We could with these different rates, we could figure out how much is in a tank, how much of whatever it is. But I don't think we really want to have to draw pictures and graphs to figure all this out. I'm sure you can expect that the equations and formulas that we're going to be given are going to be more complicated than just constants or linear. So we're probably not going to be able to find the area geometrically by looking at the picture. So we kind of need, I think, a better approach. So that's what we're going to talk about right now. In fact, I already wrote it up here. This is our approach. So for this problem right here, this is called the rate model. Okay, a model is like an equation that describes what's happening, or in this case, how much water is in the tank. So this is a model for the amount of water in the tank. And so the amount of water in the tank at any time is going to equal the initial amount, which we said was 5,000, plus the integral from 0 to whatever time we're interested in of how much water entered the tank, right? That's the entering rate, which was just 100, minus we have to take away all the water that was being taken out of the tank, and that's the leaving rate, which we said was 10t dt. So this right here is our rate model. And so we can use this to find the amount of water at any time. And we don't have to rely on geometry. We could use our calculators. Often you might be allowed to use your calculators. So we would integrate, let's see, we say 0 to 4 of 100 dt minus 0 to 4 of 10t dt. So we're plugging a specific time in, which goes in right there. This bottom limit needs to be the time from your initial condition, whatever time that was. It is often time 0, but it doesn't have to be time 0. If they told you the amount at time 1, then you'd put ones on the bottom here, and you put the amount at time 1. So this just needs to be representing the time since that value that you know. Now, we could use our calculator for this, but these are easy enough to do by hand. And so the antiderivative of 100 is 100t. And the antiderivative of 10t is 10t squared over 2, which is 5t squared. And then we get 5,000 plus, you plug the 4 in, you get 400, minus 0, you get 400. And that should look familiar. That was the area under that curve. And then if you plug 4 in here, you get 16 times 5 is 80. You plug 0 and you get 0, you get 80. That should look familiar. So we're getting the same values. And so we get the same answer, 5320 for the amount of gallons. Now, often on these problems, you're going to want to put units. These are going to be on free response problems. Gallons of water, we're going to want to get specific in describing our answers. Otherwise, we might lose credit over something as simple as not putting the units. Multiple choice doesn't matter. Multiple choice, you just got to pick the answer. So that's a pretty common question. They might ask you the amount at some point. Another really common question is to ask you about some kind of extreme scenario involving the word problem that you're doing. So in this in this case, we could say, when is the tank the fullest? That's an absolute max min issue, which is extreme value theorem, EVT, which we've used a lot this year, but I feel like we've taken a break from it. Last couple chapters, I don't think I've asked you for it because we've been doing a lot of this area and volume stuff. So how do we do EVT? Let's see. So I'm going to go ahead. This is at time 0. This is just at some time 0. I'm just going to make this a little more. So this is just sort of the general approach. I'm not going to apply it to this problem yet. We'll do it in a second. But extreme value theorem says you need to check the endpoints and critical points. So the endpoints are going to be usually described to you in the problem. So like for us, it's over the course of a day. So it's 0 to 24. So those are our endpoints. So that's usually not very difficult. I know I made it a little tougher on optimization problems earlier this year. We need critical points. Now, how do we find critical points? Again, this is a question we haven't talked about for a while, so this is just good review anyways. And this is a big deal. Critical points are places where the derivative equals 0 undefined. So we have to take the derivative of the thing we're trying to find the maximum of, the derivative of the amount. So we're going to take the derivative of this whole equation. The derivative of A0, well, that's just a number. So that's 0, right? And then the derivative of the integral of 0 to t of et, well, that uses fundamental theorem of calculus part 2, which says that derivatives undo integrals, but then you got to plug the limits in, top, first, bottom, second, and take the derivatives of what you plugged in. So we just get et when you do that, minus, same thing here, you just get lt, because 0 to t. And then we would set that equal to 0 or undefined to find critical points. Now, the 0 case is pretty common. That's usually going to be the case for critical points on these problems. So an interesting takeaway is that if et minus lt equals 0, then that also means that et equals lt. So critical points happen on rate model problems when the entering rate and the leaving rate are exactly the same. Now, if you go back up here to our picture, that was right here on the graph where those two graphs crossed. So that's kind of interesting looking at the graph of the derivatives because it shows you the critical point right there, the intersection right there, the time, not the y coordinate, that's the rate. But generally, finding critical points, we're just going to do it like we normally do. So it's the intersection point. And in our case, it was t equals 10. That was our critical point. Now we have all the places that we want to check. So extreme value theorem says, okay, you got to check endpoints and critical points, but then you got to check them all. So that's where we'd usually make a little table. It's been a little while since we've done this, and we put our endpoints and critical points in it. The table is really just a way to organize your work. You don't have to use a table. We're plugging them into the original thing that we're trying to maximize or minimize. So we're plugging them into the 5,000 plus 0 to t, 100 dt minus 0 to t of 10t dt. We're plugging them back into there. Now, if you plug 0 in, that's easy because the integral of 0 to 0 and 0 to 0 of anything is 0, and you get 5,000, which would make sense because that was the initial amount. If you plug 10 in, I'm just going to do this on my calculator because we'll often use our calculator. So I would say, okay, 5,000 plus math 9, 100 is the function, comma x, comma 0, comma 10, minus math 9, and that function is 10x. We're putting x's for the t's, comma x, comma 0, comma 10. So I just plugged everything in there for 10, and I get 5,500. And then if I want to do it again for 24, instead of retyping all this, I hit second enter and it recopies it. And I go back in here and I just change my 10s to 24s, and I get 4,520. So here's your max. Here's your min. Of course, we would write our answer nicely. The maximum amount of water in the tank is 5,500 gallons of water at time t equals 10 hours by extreme value theorem, checking endpoints and critical points. That's the kind of stuff you need to write down if it was for your response problem. Now, as on a side note, Disneyland, which is currently closed, but when are the most people in the park? And that's going to either happen when it opens or closes, which I don't think is going to be the case. When it opens, there's no one in the park. When it closes, there's no one in the park. So the endpoints aren't going to happen. So it's going to happen at some critical point in the middle of the day. And it's going to be at this weird place when the people coming into the park, the rate of people coming into the park is exactly equal to the rate of people going out of the park. So it's kind of weird. It's this moment when this is the same amount of people are coming in and out at the same time. That's actually when the park is at its highest or at a peak during the day. And one of those peaks is going to be the absolute max. So I think we should probably go and investigate that, ourselves. So maybe, maybe next year in Calc BC, we'll take a trip to Disneyland and figure that out if you stay with me another year. Okay. On the back, we're going to go ahead and just try a free response problem. It's pretty old, 2003. It's a graphing calculator problem. So whenever I put GC, that means graphing calculator. So we're going to have our graphing calculators ready. So a tank contains 125 gallons of heating oil at time zero. That's your initial condition. So I often use capital A for the amount of whatever it is we're talking about. Sometimes they'll give you a letter to use, so you should use it. But this is A0 equals 125. So I like to, as I read this, summarize the important points into really shorter notation. And it says during the time on 0 to 12 hours, those are probably going to be our endpoints for something, and we shouldn't give answers outside of them. Heating oil is pumped into the tank. So this is your entering rate. So I put a plus next to it just to remind myself I need to add that. And this is gallons per hour. During the same time, heating oil is removed from the tank. So this is going to be the one that we're going to have to subtract. That's the outgoing rate. That's the leaving rate. So probably one of the first things I would do, because we're going to probably be doing multiple calculations involving both of these equations, and I don't want to have to retype them every time. I'm going to type them in one time really well into my calculator. I'm going to put them into the Y menu. So even if I have no intention of graphing these, I'm still going to put them in the Y menu so that from the home screen, I can quickly call them using bars, Y bars, Y1 or Y2. So I'm just going to put them in order here, 2 plus. Now be careful when you enter this in. You definitely need some parentheses to ensure order of operations. You need parentheses around the whole denominator. And then there's parentheses. We're putting X's for the T's. And there's parentheses built into the natural log. Close them. Close parentheses on the bottom. Don't forget the 2 plus at the front. Okay, the next equation is going to be 12 sine parentheses x squared divided by 47. Make sure you're in radian mode because we got trig here. You get the wrong answers if you're in degree mode on the AP test. So I put those in. Now we could go ahead and graph these if you want. I usually won't graph them, okay? But you could graph them, and you could get a graph like the one we did on the front. Now to help the graphs to be more, you might put Y1 here as a note to yourself and Y2 as a note to yourself there so you remember which ones are which. If you want to graph both of these and you want to be able to tell which one is which easier, it's going to graph the first one you put in first, so that kind of helps. But you can also go over to the left side and make your lines look different. You can make them thick, you can make them shaded above, shaded below, you can do stat plots, you can do dash. So I'm going to make it thicker, the first one thicker, just so it's easy to tell. Usually I'm not going to graph these, but I just made a horrible mistake. I should have gone to window first because now I'm going to get some graph that is not what I was hoping for. So I need to go to window. The X value is going to be 0 to 24. I don't know what the Y value should be, so I could go after I enter the X values that I want to use. I can go to zoom fit, zoom 0, and that'll now it takes a little while longer. It pre-calculates all the Y's based off the X window you gave it, and then it resizes the graph so to fit it. So that's the entering rate of heating oil, and that's the leaving rate of heating oil. Now, actually, I put 0 to 24, but I should have put 0 to 12. I just was in the mode. So I'm going to go back. I really don't want to see more than what I'm supposed to see, because I might then be tempted to put answers down that I wasn't supposed to put down. Now, going back, my window, I'm going to adjust the window, the y value to -1, just because it made it bigger because I did 0 to 24 originally. So this is the drawback of graphing, is that you kind of fool around with it a lot to get a nice view of it. So a lot of times I avoid graphing, but this is our picture. I'm going to go ahead and draw that. Hopefully you're following along on your graphing calculator right now. I'm going to draw that right here, and then we can talk about some of the things that are going on in it. So this is time. This is gallons per hour. The graph looks like. So that's the first graph, and I'm going to label it. That's HT. And then the other graph is like this, and kind of like that. So that's RT. Now this is the entering rate. So right here, the difference between these is a net gain of heating oil between those times. But then the leaving rate's more than the entering rate. So this is a net loss of heating oil. And then here we get another net gain. Not that I would usually show all that, but that just, I don't know, it's just kind of interesting. Okay, what I'd probably do right away, because I've recognized that this is a rate model problem, is I'd probably just go and try and write my rate model. Okay, so my rate model, and this isn't, I don't even know if I'm going to use this right away. Probably won't use it until like a later part, but I think it might just be good to write it down, because the whole problem is kind of based off this idea. The amount of heating oil at some time is the amount at time 0, which is 125, plus the integral from 0 to whatever time we want of the entering rate, which we can just write HT dt. I don't want to on free response questions, you don't have to rewrite this. You can just use the name anywhere in your work, minus 0 to t of RT dt. Now don't put E and L for entering and leaving if they give different names for it. This is our rate model right here. This is what a rate model is. Okay? Now, on part A, they say how many gallons of heating oil are pumped into the tank from 0 to 12. Now, it's not asking you for the total amount of heating oil in the tank at 12. It's just asking what's going in. So that's just a specific part of our rate model. That's just 0 to 12 of HT Okay? And you can just write that. If you really want, you could write 0 to 12 and put that whole complicated expression, but I wouldn't do that. But you can if you want. I would just do this. Now, this is the setup, and that's worth 1 point out of 9 points. And if you don't put it, you're losing that point, even if you get the right answer. You have to show the setups. And this is something I've been requiring on my tests. If you can use your graphing calculator, you have to show the setups. You got to show the calculus. So it doesn't mean you have to show me the buttons you're pushing or whatever. So I'm not going to do this on this screen. You could, but I generally just integrate on the original screen. So I'm going to do math 9. Now, I don't want to retype that crazy thing there. So I'm going to do vars, right? Vars right here, vars. And then we're going to go to y vars. And we're going to go to function, hit enter, and then y1 is the function we want. And so then that copies and pastes the formula from the y menu. So I'm going to take advantage of that a lot of times on problems. Comma x, comma 0, comma 12, hit enter. And we get 70.570 or 70.571. Just give me one of those answers. And maybe we could say gallons of heating oil. So that's units. Gallons of heating oil are pumped into the tank from time t equals 0 to t equals 12 hours. This is a really nice, thorough answer, okay? And you might need that to make sure you get all the points. So often they ask you to write your answer in the context of the problem using the correct units. So that often means you also need to talk about what times are involved and put the units of those time. So that's just a really good answer. Part B says, so this is kind of typical. Part A, they might just ask for the total of one of the rates. Part B is the level of heating oil in the tank rising or falling at time equals T equals 6 hours. Give a reason for your answer. So is the amount of oil in the tank increasing or decreasing, rising or falling? And I already looked at this picture. You could tell it's rising here, falling here, and rising again here, right? Because so it really just depends on the entering rate versus the leaving rate. If the entering rate's more than the leaving rate, then the amount of oil is increasing, going up. If the amount being taken out is more than coming in, then it's going to go down. It's going to decrease. It's going to fall. Now, we could look at this picture, I guess, and figure out where time 6 is, but you're really going to need to support your answer. So I would say the best way to figure it out is to figure out, well, what's H6 and what's R6, because that's what you need. You need the entering rate and leaving rate at time 6. Now, I've already entered those equations in my calculator, so I don't have to retype them. If they're in the Y menu and you just want some quick values, you go to the table, which is second graph button on my calculator, and it brings you to the table. Now, there might be a bunch of stuff in here from the last time you used it. So we could just type 6 in here, and it gives you the values right here, and it shows you more precise, accurate versions if you highlight them. So I'm going to write those down. So that's the quick way to do this. Use your calculator and not have to retype stuff in. So this is 5.394 in gallons per hour. And then the other one is 8.318 gallons per hour if you truncate. You could round them if you want. And so I think it's good to write those down. And now looking at this, the removed rate is bigger than the entering rate. So it's going down. So we're going to write something along those lines. We're going to say, the level of heating oil in the tank is falling at time t equals 6 hours. So that's your answer. But then I want you to kind of support your answer. You have some numbers in your work that kind of help, but I want you to explain how you made your decision based off those numbers. And so you could say, since the oil is being removed at a greater rate. And so you could I'd put the number there, 8.318 gallons per hour are the units. I'm trying to put units on here at a greater rate than the oil removed, which is at 5.394 gallons per hour. So this is a really good answer here. Now, another way there's other ways you could have answered it. You could have actually said, what's the overall rate at time 6? And so the overall rate, and we wrote this before, is going to end up being the entering rate minus the leaving rate. When you take the derivative of your rate model, that goes to 0. Fundamental thermodynamics part 2 ends up just giving me HT minus RT. So you could do this and calculate this value instead, and it would involve these numbers right here, but you would subtract them. So that value, what it would do is it would come out to a negative. gallons per hour, and that'd be the overall rate of change of the oil in the tank. And so you could say, oh, it's falling because the amount of oil is decreasing since the overall rate is negative. You would say something that because it's negative, that it's decreasing. So, okay. That's kind of a typical question. A lot of times on rate models is they ask you about the overall rate or something. Now, part C says how many gallons of heating oil are in the tank at time 12 hours. So part C is the most straightforward question where we're going to use our whole rate model and just find the amount of oil at time 6. So we got to show our work. A6 equals 125 plus 0 to 6 of HT dt minus 0 to 6 of RT dt. That's your setup. That's worth often more points than your final answer. So, in fact, this whole problem right here is worth 3 points on part C, but this right here is 2 of those points. And your answer is 1 point. And you're just going to use your calculator to find the answer. On the previous part B was 1 point total. Part A was 2 points total, and 1 point for the setup, 1 point for the answer. Sorry, you guys can't see that. So you got to show the setup. Okay, even if you write the right answer, you're going to get 1 out of 3 points if you don't show the setup. So you got to show the setup, you got to show the limits, you got to write DT, you got to write all that, label it nicely. So I'm going to do this on my calculator. I'm going to go back to the home screen, and I'm going to do 125 plus math 9. So I'm going to just type it in, all one big command line. And so 125 math 9 vars y vars function y1 comma x comma 0 comma 6 minus math 9 vars y vars function y2. Make sure you do them in the right order, comma x comma 0 comma 6, and I hit enter, and this is going to give me the answer. So let's see, 147.637 rounded or truncated comes out the same. Gallons of heating oil in the tank at time T equals 6 hours. That's a kind of a thorough answer with units and context. All right. So that's usually a common question. They might just ask you to do the rate model, straightforward, plug in a time, find the overall amount. And then part D is a really common question too. Part D says how many gallons of heating oil at what time T for 0 to 12, so those are your endpoints, is the volume of the heating oil in the tank the least? Show the analysis that leads to your conclusion. So this is extreme value theorem. We're looking for the absolute minimum, the least. So we're looking for absolute minimum and absolute minimum of the amount. Our endpoints they gave us explicitly. Sometimes they might say over the course of a day, and so you'd have to say, oh, that's 0 to 24. We need critical points. This is all work you should write down. Critical points, write the word critical points down. Don't abbreviate it. Don't write CP. How do we find critical points? If you just give me the critical points and you don't show me the calculus that leads to them, then you might lose some points. So the way you find critical points is take the derivative, and that's going to equal, that's the derivative of our rate model. So the derivative of 125 0, the derivative of this, the derivative of the integral undoes it. You got to plug limits in, take the derivative of them. It's just going to be HT minus RT, and that's not enough. You got to write equals 0, undefined. Okay, if you don't write that equals 0, you might lose a point. That's critical, important information. That's how we find critical points. It's not just the derivative. It's the derivative equals 0. Now, the way I'm going to figure this out is you could go to your graph. If you did bother to graph it, it's going to be the intersections of those curves. So you could go to the graph and say, all right, well, you see two of them. I mean, that's, you can do second calculate, intersect, first curve, second curve, guess. And so it's just the time value that we want, just the x value. So that would be t equals 4.790051. I'm carrying extra decimal places because we're going to use this in a future calculation. Second calculate, number 5, intersect, first curve, second curve. Now you could also enter a number in. This is 0 to 12, so that looks like it's around 11. So you could just type 11 in instead of wasting time moving the cursor over and over and over. And it's this x coordinate right here, that's the time, 11.31847. Okay? And so those are your critical points. The other way to do it, if I hadn't bothered to graph it, I wouldn't have done it this way. I probably would have graphed, and we could do this. We could go in here, turn these off, and I probably would have graphed ht minus rt. So we could actually, in the graphing menu, do vars, y-vars function. ht was the first one, minus vars, y-vars function, y2. I would have graphed that equal to 0. I find it's easy to solve equations if you set everything equal to 0. And then you go to window and you want 0 to 12 still, but all you care about are the x-intercepts of that graph. So I don't need a big, beautiful version of it. So there's one critical point, and there's the other one. And if you do second calculate 0 now, you say, well, that one looks like it's between 1, 2, 3, 4, and 5, like 4.5 to 5.5, guess 5. And hey, same answer, right? We got before. Second calculate 0. That's between 11 and 12, guess 11.5. So we're going to find this one right now. And 11.31847, that's the same value we got from the graph. So either way. But you need to write this stuff down, okay? And now we're going to make our table. So we're going to make our table. T, we're plugging them into the actual amount, the rate model. So I would rewrite that just to help myself not plug it into the wrong thing. And we're going to put the endpoints in and the critical points in. Remember, write more decimals than 3 decimals if you're using it to calculate other things, okay? Now, 0 is easy. That's 125. And then I did the wrong thing on part C. Part C, I said it asked for 0 to 12. It said 12 hours, and I put 6 in for some reason. I think I was in the mode of the last problem. So let's change that real quick. And let me write down what the right answer is for that. Plus, that's going to be one of the values in our table. So you don't need to recalculate it if you've done it correctly first. So going back to the home screen, I'm going to redo that calculation and put 12s in for the 6s. Now, if you want to insert a value and have everything else push over so you don't have to retype it, you do second, delete, insert, and then whatever you type in screws everything over so you don't have to retype it. So this is what I should have done on part C. My answer should be 122.025 or 026. And then that's what I would put in my table right here, 122.025 or 122.026 if you want to round. So I did the wrong time on part C, but that's also, now I got to do these ones and I'm going to plug them into this whole thing, but I don't want to retype all this stuff. So I use that trick, second enter, and it copies and pastes it. Now for the 12, I'm going to put 4 point, and I don't want to retype everything. So I hit second, delete, which is the insert 790051, and it moves everything over. And then down here I put 11.31. Oh, wait. I got to put the same thing in both of them, 4.790051. So this is going to give you the amount for this one, 149.407 or 149.408 if you want to round. And then I'm going to do it again and then replace those fours with 11.31847. 11.31847. And I get, take a deep breath, calculate slow, 120.738. Round truncated is the same. So make use of your calculator. Don't retype everything. I put those equations in the Y menu so I could do vars, Y vars often. I'm recopying previous commands. So we're looking for the minimum. So watch out. This is the max, which is not what we want. This is the minimum right here. So we're going to write a nice answer with units and justification. All this stuff is stuff that we need to get full credit, but also our final answer needs to be written nicely. So we're going to say the volume of heating oil in the tank for 0 to 12 hours is the least, and I always write what that value is. It's 120.738 gallons. Got to put units. At time t equals 11.318. 3 decimal accuracy for your final answers. Hours, units. So that's a really good description of your answer, but let's justify it by extreme value theorem. Write it out. Don't initialize it. This is free response. Don't be lazy. And how does extreme value theorem work? Because usually just naming the theorem isn't enough by itself. You need to explain how it works by checking endpoints and critical points. This is what you need to strive for on free response. Okay, we're going to be doing a lot more free response. So this is what you need to strive for. Your answers on free response. Describe well, units, specific times, name the theorems, describe the theorems if you want to get full credit. Now, by the way, this part was worth 3 points on this particular problem. And the points were given. 1 point was for writing this down, for writing that the derivative ht minus rt equals 0. If you didn't have that, if you didn't have equals 0, you lost that point. Also, this is a good lesson in that even if you don't finish the problem, if you'd written that, you'd get a point. So try it, okay? And then 1 point for your work and 1 point for your final answer. And those all add up to a total of 9 points. So, okay, try the homework. 11.5. You guys get some free response questions. Rate models are really just kind of word problems with fundamental theorem of calculus part 1 applied to them, right? You are now what you were before plus the accumulation of all the changes. The amount of oil in the tank now is the amount of oil in the tank before at time 0, 125 gallons, plus the accumulation of all the changes, positive changes, minus all the accumulation of all the negative changes. So usually rate models have 2 rates involved, and it's applied to a word problem, but it's really just fundamental theorem of calculus part 1. Okay?